Hi guys, in this video we're going to talk about key features of rational functions, specifically what is called points of discontinuity, which can be vertical asymptotes or holes in the graph. So the parent function of a rational equation is just y equals 1 over x. And so rational functions are a ratio, which means it should look like a fraction, and there can be any type of polynomial in the numerator or denominator. So the most basic one is 1 over x. So the reason that there are gaps or breaks in the graph of rational functions is because there is a number that you cannot divide by. So think about, what number do you think we are not allowed to divide by in math? If you said 0, you would be correct. X cannot equal 0. So what happens is it creates a gap in the graph because we literally have to skip over that number. If you were to look at the table, when x was 0, the y column would say error. It's impossible to figure out that value. All right, and as always, y'all, these are your notes, so you should be copying these down. All right, and I'm going to also show you Desmos so that you can see what it looks like on there. So here's that same equation graphed. And it's a little bit hard to see, but there's my vertical line when x equals 0. All right, and again, the reason that that is showing up is because you are not allowed to divide by 0. So we literally have to skip over that number when we are evaluating, and that is causing a break in the graph. All right, so the second example, we have a function 5 over x minus 1. So again, the points of discontinuity occur if your denominator equals 0. So this is not supposed to equal 0. So what number are we going to have to skip? What number will make the denominator 0? If you said 1, you would be correct. For this particular graph, when you looked at x as 1, it would say error on the graph. And there would be a vertical asymptote at x is equal to 1. And a graph should look something like that. You can go over to Desmos and check. So there's my new graph. I'm going to zoom out a little bit so that you can see. And if I make my vertical asymptote 1, you can clearly see that neither side actually touches that green line, but that green line splits it right down the middle, so that is our asymptote. All right, another example, we have x minus 6 over x plus 4. So try this one. Where do you think I'm going to have a vertical asymptote? Where do you think I'm going to have that break in the graph? If x plus 4 is not allowed to equal 0, x cannot equal negative 4. Negative 4 is going to be the one I have to skip. All right, so I'm going to pop over to Desmos so we can see what that looks like. And if I make my vertical asymptote go to negative 4, sorry, they're both green, but you can see that dotted line is my asymptote, and it is separating the two sides. All right. So what's a little bit different about the second one? Or sorry, the third one. What's a little bit different about this one? This one has 2 factors in the denominator, which means there will be 2 x's that we're not going to be able to use. There's going to be 2 numbers on the x side of the table that will say error in the y side. So x minus 2 cannot equal 0, and x plus 4 cannot equal 0 as well. So on one side we have x cannot equal 2, and on the other side we have x cannot equal negative 4. So I'm going to graph it, but I am expecting there to be a vertical asymptote when x is 2 and a vertical asymptote when x is -4. So let's see if we're right. So I need to pull up another one. X is equal to 2. Change that to dotted real quick. And you can see those are 2 vertical asymptotes. Those 2 imaginary lines, it separates the sections of the graph. They never touch it, they never cross it, because we literally are going to have to skip those numbers. Those numbers make the denominator 0, so we have to skip them. All right, so the next one we're going to do in a little bit of a different order. The next one is x minus 2 over x squared minus 6x minus 16. So how many asymptotes do you think this one will have? Do you remember what to do with something like x squared minus 6x minus 16? Does that look familiar? All right, so I'm going to come over to Desmos, and I have that one already graphed. Oh, and I lied. That was fine. But this is the example I wanted to do. Sorry, y'all. But that's an easy fix. I wanted it to say x squared plus 6x minus 16. X squared plus 6x minus 16. So you might expect that to have 2 vertical asymptotes as well, because x squared can be factored into 2 binomials. So there should be 2 points of discontinuity for this. But if you look, this graph actually only has 1 vertical asymptote. And that is when x is equal to -8 is the break in our graph. So I was expecting there to be 2 because my denominator was quadratic, but I can actually only see 1 vertical asymptote. So that doesn't mean that there isn't another point of discontinuity. It just means that it's not an asymptote. Let me try to get this into screen. Let's see if this works. So you see here on my table, I do have an undefined value when x is positive 2.
Teachers and students, please pardon interruption. At this time, if there are any students in the 7-800 building that do not know what bus they need to ride this afternoon, please come to the office at this time. Only the 7 and 800 building. If you have any students that need to know their bus number, please come to the office at this time.
All right, so I still have 2 points of discontinuity, but I can't physically see the other one. That's because that is showing up as a hole in the graph. A hole is so small that we cannot see it visibly as a break in the graph, but it exists as a break in the graph because we cannot plug that number into the equation. So if you are a step ahead, if you already factored x squared minus 6 or x squared plus 6x minus 16, that would be x plus 8 and x minus 2. So I still have those 2 points of discontinuity. X cannot equal -8, and x can also not equal 2, but can you see why the 2 is not visible on the graph? The 2 is not visible on the graph because there is an x minus 2 factor in the numerator that will cancel that factor out. So the fact that that cancels, we call this a removable discontinuity because I can remove the factors, and that is turning this one into a hole in the graph. All right, so we have a vertical asymptote at -8, but there is a hole in the graph as well. I'm going back because I don't remember what this looked like. Okay. So I'm going to skip that for a second. there's a hole in the graph when x equals 2.